Learning table joins is often the most difficult hurdle to get through when learning SQL. Today, we're going to practice through it. By learning joins, everything in SQL becomes possible, and it helps you understand the relationships of data structures in any database you're working with. Let's start by looking at the operations and resources relationship in our database. I have a nice diagram here that explains in the chocolate factory how operations and resources are related. If you can imagine, a manufacturing process might have 5 steps. In this case, mixing, baking, cooling, packaging, and inspection. These 5 steps are the core of how things get made in the chocolate factory. However, each of these steps may have many different workstations or physical machines where that operation can be performed. And so we see these 2 unique types of entities that are extremely related. If we look at the baking resources, let's imagine these each represent an oven. There are 4 ovens, maybe oven 1, oven 2, oven 3, oven 4, and they're all associated with the operation baking. So if we look at these tables in our database, it's easy to see how they might be related. If we look at MES resources and run this, we'll see that there's a column which very clearly references an operation. This is called a secondary key. And when we run the same type of query on the operations table, we see what is just called the primary key, right? Now, you'll notice in the operations table, the operation ID is just called the ID. And so now we can connect these 2 tables on their secondary and primary key relationship using, most commonly, an inner join. So if we type select star from MES operations, inner join MES resources, we're designating the 2 tables that are going to be connected. And now in SQL, we have to annotate which columns to connect them on. So what you'll do is you'll write inner join MES resources on, so this is the new syntax, on MES resources dot operation ID. Remember, that's the column that has the secondary key, and we're going to join that to MES operations dot ID, the primary key. And so now if we run this query, we're going to get every column from both tables joined on these clauses. And you'll notice that even though the operations table had about 5 rows, we're getting results for as many rows as there are in the resources table. That's because the join is able to find a match for every row in the resources table. Now, this can look a little confusing, and this code can be a bit hard to read. So most of the time when you're working with joins, you will alias the tables that you're working with. So what you'll see very commonly is a letter like O for operations and a letter like R for resources. And so now we've sort of nicknamed these tables. And when we write our joins, we can write much shorter queries like r.operationID equals o.id. Now, if I run this, I'm going to get the exact same results. But what I can start to do to make this all much more refined is define the columns that I actually want to see. So with a query like this, I would probably want the r.id. So I want my resource ID. I want the resource name. And then from that join, I now have access to the operation name, right? And so here, I'm getting a result that's much easier to read, much easier to sort. For example, if I wanted to filter where operation name equals baking, I can run this filter, and it's going across both tables and creating a refined output of exactly what I'm looking for. So even if I didn't know the ID of that operation, by using this join, I can filter to only resources in the baking operation. Okay? So let's take that, note this syntax, and let's try to apply the exact same concept to 2 different tables. So there's an MES complete logs table that contains an operator ID. Give this a try, pause the video, and see if you can perform the same type of join from the complete logs table to the MES operators table. Okay, so hopefully that wasn't too hard. The idea here is very similar. We're going to select everything from the MES complete logs table. Let's take a look, and we see there's this column called operator ID. So we know that's what we're going to want to join on. So let's clean this up. Select star from MES complete logs, and let's call this CL for complete logs. So we have an alias. We're going to inner join on inner join MES operators. We'll call that O on CL.operator ID equals O.ID, right? The ID for any table, if it's its primary key, is just going to be .ID. And so now when we run this, we'll get a full output of the complete logs, but we'll see if we scroll to the right, we have all the information from that operators table as well that has been joined where the operator ID connects to the primary key from the operators table. And so now, to create a more refined view of this type of thing, we will do maybe cl.resource ID, cl.timestamp, and o.operator name. And so now we're getting a very clean log of who performed which completions at what time. Now, you're probably wondering why this is all necessary, right? The complete logs table maybe should just have the operator name. And this gets into the concept of normalization and why databases store data like this, right? So if you think about this join that we just did, there's a complete table that connects to an operators table. And in our situation, this could probably have just been one table, right? We could have added the operator name in that table. But in a larger database, there's usually a lot of additional columns that are really just connected to the operator. And so by separating these tables, let's say maybe there was the operator's start date and the operator's last name and the operator's email address, starting to put that information into every table that references an operator is going to be a ton of columns, which is going to add complexity and storage cost. So these are the two main reasons that most information is usually structured in separate tables, right? So the operator's information is only going to be stored in this operator table. And the complete tables, or any tables that reference an operator, is just going to store that operator ID. That's because now that we have these inner joins, we can start referencing any data that we need very easily as long as we know the primary key and secondary key. All right. So we just did this where we're going to look through the name of the operators. Let's take a look at another very cool example of a join, just to really drive home the concept. When I look at our ERP bill of materials table, it's another table where we see lots of useless IDs, right? To a human, these IDs don't really provide much information. But we now know that we can alias this table and perform an inner join to ERP products on P on bomb.product ID equals P.ID. So this is the same exact type of join. Let's maybe clean it up a bit. Normally syntax will look a little bit more like this. And we can now create a refined output which uses information from both tables, right? So the most common thing you'd probably want to do here is get your maybe bomb.id, bomb.id, material ID, and you want to bring in that product name which lives on the product table. So when I run this, I'll get a much cleaner view of the products and what goes into them. Now, this material ID leaves a lot to be desired as well, because we want to see what that material is called if we're actually making a report. And this is where joins start to get pretty cool. The materials and the finished good products, right? So the products are fudge, brownies, chocolate chip cookies, and chocolate bars in this database. The materials actually live in that same table. It's called products. So if we want to join to material ID, we can actually do this exact same join. So let's copy. And we can create a second reference to that table. In this case, let's call it M or MAT for material. And so instead of joining on product ID, we're going to join on material ID, right? And so now we have this second table where we can pull in any information just like we could on P, and we can pull in M dot product name. Now it's a little confusing because we are calling the product, but the material seems to still come from the products table. This is an example of when databases might not always make the most sense, and you sort of have to navigate what they are based on what you see. All right, when we run this, we're going to see an error. I didn't use the right alias. So I was trying to reference m.product name, but there's no tables that are called m. I'm going to switch this to Matt, and now we see, right, we have the ID, the product name, and the product name 1. Now Hex has conveniently created a unique name for that column, but realistically, if we were writing a report like this, we probably want to write our own alias for that column called material name. And so now, the same as usual, we can start to build filters and sorting all on top of this table that we're bringing back to create reports on how much fudge requires of certain materials, and we can filter it using the English names that we're familiar with. So, quick practice problem just to keep on chugging. Again, this concept is going to be learned best by using it over and over again. Let's display a list of work orders and actually find the product name that is associated with that work order and filter by chocolate bars. Okay, so select star from ERP work orders. Always a great way to get started. Let's look at this table, and we'll probably see a product ID column, right? So we want to join on that product ID. So let's label this first table work order. Inner join ERP products. So that's the table which we know has the product name on work order dot product ID equals p.id. Now I want to quickly point out that this join order does not matter. There is no standard here. If I were to switch this to p.id equals wo.productid, the output will be the exact same. All SQL is doing is finding the rows of these tables that match, and it's joining them. Okay? So lastly, I would apply a filter where p.product name equals chocolate bars. Okay? And so now, if I run this, these work orders are all returning and they all have the same product ID, which I'm guessing is probably chocolate bars. Let's clean up this output. So let's do work order.id as work order ID. P.product name should be chocolate bars, and maybe planned start date. So work order dot planned start date. And voila, here are the work orders that are for chocolate bars. And so let's take a look at some more tables that are definitely connected. If you could look and join the products and the route steps table, sort by the product name and then the operation sequence from the route steps table and identify which products don't use all 5 steps in our factory. All right, so let's do select star from, let's go ERP route steps table. Let's just take a peek. And let's see, ERP route steps. That's an error you'll see, ERP routes. And this should list out, again, we see this secondary key, so we know we can join to something here. So let's do where R is the name of our routes table, and let's add an inner join ERP products, we'll call this P, on r.productid equals p.id. So now we know that we have access to everything in the routes table and it's extended to the products table. What we can now do is maybe order by p dot product name. And so if we run this, we're going to get a list of routes that is sorted by the product name, right? Now, just a reminder, Hex will cut off this preview pane at 10 rows. This is just for sort of practicing. If you switch over to display, you'll get the full query from Hex. So we can see there are 17 rows in this data set. And so let's keep looking here. We want to sort by product and then operation sequence. And the operation sequence lives on the route. So if I do r.sequence, sorry, it's called just sequence in this table, we're now going to get a sorted list for each part of which operations it goes through. And we can see that the product called brownies comes first. Now let's add some columns just to make this easier to read. Instead of select star, let's do select p.product name, and then we'll do r.sequence and r.operation name. And so now we'll get a very clean output of each of our products, the order of steps that it goes through, and the name of those steps. So we can see now the chocolate bars does not appear to go through baking, which makes sense. The chocolate chip cookies go through all 5 steps, and fudge apparently only goes through mixing, cooling, and packaging.